All right, good afternoon. If we do have anyone online, please go ahead and ask a question so that I can see that you're there and so that I can hear that you can hear me. Everything should be working, but you never know. All right, we've got lots to cover today. We're going to cover not only confidence intervals, but I'm going to get into the t-distribution as well. So it's a pretty full class. Starting to move a little bit faster than we have so far. So let's see anything on the Hangouts here though. Okay, yeah, it's there. Oh, hi, Annie. Okay, so I will still briefly review sampling distributions because they're key to thinking about everything that we're doing almost from now on. And then I'm going to talk about how to calculate confidence intervals for a population mean based on the central limit theorem, and briefly also for a population proportion, which is basically the same way. And then cover the t-distribution for estimating confidence intervals from small samples. Next class, we'll get into hypothesis testing and cover all of this from a different perspective. So today is about inference, about estimation of a population quantity from a sample. Next class will be about inference of a hypothesis test. So you recall we talked about populations and samples, population being composed of individuals and samples being composed of groups of individuals that are obtained in successive random samples. And if we have a population distribution that looks something like this broad peak, if these are serum cholesterol levels, and if you take repeated samples from that population and look at the average of groups, you'll get a much narrower peak in the sampling distribution of averages. And that's because there isn't as much variability in a group average as there is in individuals, right? And the central limit theorem relates those two distributions, the population distribution for individuals and the sampling distribution of sample means. And the three key components of it were, one, that the mean of the population and of the sampling distribution are identical. The second, that the standard error, that is the variability of the sampling distribution, is equal to the standard deviation of the population distribution divided by the square root of n. And this is true in the large sample limit. In the large sample limit, it doesn't matter what your population distribution is. This is what your sampling distribution will be. It'll be normally distributed with this standard deviation. So the important thing that tells you, besides that precise relationship, is that the larger the size of your samples, the smaller your standard error, which makes sense because you can imagine if you're just taking averages of, say, groups of 3 people, there might be quite a bit of variability. If you're taking averages of the cholesterol levels of groups of 1,000 people, it's going to be less variable, at least if those samples are taken at random from the same population. With proportions, there is a slightly different formula for calculating the standard error. It's this square root of your proportion estimated from the sample times 1 minus that proportion divided by n in the square root. But other than this different equation for estimating the standard error, the methods that we'll use for the mean of a continuous variable or the proportion of a binary variable will be the same. Here's just the review of it again, the important part here. Oh, geez, what happened? My goodness. Okay. Being that this sampling distribution is normally distributed, we know given a population distribution where we know the mean mu and the standard deviation sigma, we know that this will be the distribution of the means of successive samples, as long as those samples are sufficiently large. It'll be centered at mu. It'll have a standard deviation that is what we call the standard error. That's the standard deviation over square root of n. Everything okay so far before we move on? Okay. On to estimation of confidence intervals. And I just sent out a little fun survey for you where you get to guess my age. If you fill that out, I'll analyze it later and discuss it. I have used that in previous classes before. So I am going to use it for a couple things, I think, this semester. I'm going to use it. So first of all, it's useful for getting you to think about what is a confidence interval. And a lot of people it takes a little while to get the hang of that. Second of all, I can test the null hypothesis that I appear 1 year older than I did last year when I taught this class. So I'll see, or maybe the null hypothesis is that I haven't aged at all. I don't know, we'll see. It'll be interesting to find out. So fill out the survey. It takes literally like 15 seconds. Well, no, take longer than that because you should think about it as you do it. Think about what I mean by this confidence interval. So when we calculate confidence intervals, there's going to first be this so-called point estimate that is a single number that represents the center of your best guess. So if you're going to guess my age and just give a year, that would be your point estimate. You'd say, that's what I think it is. But that doesn't tell us anything about your uncertainty in that estimate. If you happen to know what year I was born, then that's all you need. There's no uncertainty in it. If you know my age, then you're cheating. If you fill out the survey, you have to try to, I don't think you should, but all bets are off if you actually know the answer. This is about uncertainty in your answer. So that's where the interval estimate comes in. You don't know what the true answer is. It's a way of quantifying that uncertainty and saying, giving an interval of plausible values, a minimum and a maximum, where you can give a precisely defined level of confidence that the true answer falls range. So if here is your point estimate, and then maybe between here and here would be a confidence interval of a certain amount, depending on how confident you are in your ability to guess ages. No, I just put those. I just put those on there. Yeah, maybe I shouldn't have put any numbers on there. I don't want to bias your guesses. Yeah, no, there's no guarantees that my age is within those ranges. So here's a motivating example, other than guessing someone's age, which is not really going to come up most likely. We're doing a study of birth weights of infants. Take a sample, let's say 309 infants. I don't know why that number, that's just what the sample is. And this is a random sample of a population of interest. We calculate the mean of this sample. We get some value that, I should get this to stay put. can't really use the mouse without changing slides. Okay. That mean of the sample is going to be our point estimate. Do you remember why in terms of the central limit theorem? Which one of those three aspects of the central limit theorem would tell us that the point estimate should, in this case, be 119.6? Sorry?
Is the mean of the sampling distribution is the same as the mean of the population?
That's right. The mean of the sampling distribution is the same as the mean of the population distribution. So even though our sample is not perfect, it's our best guess. And as long as it is a random sample, we can assume that it is an unbiased estimate, the sample mean. So we also estimate the standard deviation, or actually maybe we for some reason know it from the population from some much larger study. More often it will be estimated from the sample. So then the questions that we want to know, what is the average birth weight of infants in the population? That would be the point estimate, which you just said. And the second part, what is, for example, the 95% confidence interval on that average birth weight? And note the big not here. This is a distinct question from what interval contains the birth weight of 95% of all infants in the population. Can you see the clear difference between question B and the not here? Because I can tell you right now that there will be some questions kind of, you know, prodding to see if you get this distinction on the exam. And last year, a lot of students got that wrong. I'm hoping, I'm still going to ask, but I'm hoping that you'll understand it better, because I'm really going to try to hammer it in this time. That the confidence interval is about the sampling distribution, not the population distribution. So it's about the distribution of means, not the distribution of individuals. Is that clear? All right. So given a sample where we can calculate the mean and the standard deviation, we can construct a confidence interval. The confidence interval comes from the point estimate, which will be the sample mean, and a so-called margin of error, which is the uncertainty above and below the point estimate. It's not quite the same as the standard error, but it's related to it, and we'll get to that. One way you can do this is just from a web page. Here's one that you can use. I actually do recommend taking a look at it, because it makes it very easy to just play with the parameters and see how the confidence interval changes. So you'll notice the input variables here, a mean, a standard deviation, and some limits here on the T or the Z statistic. So this is really, they're not doing everything for you. This is just providing sort of a shortcut to using one of the tables. So the margin of error is how far above and below the point estimate you have to go to have a certain confidence. For a large sample, or for a sample where, and by large here I actually mean really large, I don't mean n equals 30, and I'll show you what I mean about that later, but where the standard deviation is known precisely from the population or from a very large sample, the standard error for the 95% confidence interval will be 1.96 times the standard error. And you will use a table of Z values or of T values to look that up if the sample is smaller, or if the or if you want some confidence interval other than the 95% one. Using that Z distribution works, again, if we have a large sample, and Actually, the n greater than equal to 30, I don't actually recommend that, and I'll show you what I mean a little bit later. I would say more like n greater than 300 or something here. Or sigma is known. It turns out that I mean, it's not a big difference, but the t and the z distribution, I'll get to the t distribution soon, are kind of different unless you get to a very large sample. So it's pretty formulaic how to calculate a confidence interval. Here are your instructions. Just take the sample mean plus or minus some factor times the standard error. And these are the cases if we know the population standard deviation. And there's an equation here for a proportion as well. And I put a link also on the Blackboard page where I did a little short YouTube video just showing how to go through this by hand. It's like 3 minutes if you wanna see that. So the calculation of the confidence interval is pretty straightforward. It's the interpretation that you need to be careful about. So something that it does not do is imply a 95% confidence interval does not imply that 95% of the population values lie between these limits. Is that clear now? You see, is anyone unsure about that? This is about uncertainty in the mean. So like group level characteristics, not individuals. And it does not account for bias in the point estimate. If we have a biased sample and non-representative sample, it does not, the confidence interval will not help us correct that. It'll put an uncertainty that's an equal amount above and below our point estimate. If the point estimate is biased, then this can't help you. What it does do is it gives you an interval where you can be 95% confident that the true mean or the true proportion for the entire population lies. So that's pretty cool. You take some information from a sample and it tells you precisely in the face of uncertainty how confident you can be. How big an interval you need to be this confident, how big an interval you need to be this confident. And it can also be interpreted that if you were to repeat this study, repeat this sample 20 times, if it's a 95% confidence interval, then that confidence interval would contain the true mean 19 out of 20 of those times. So this, of course, is not sort of error in the population mean itself. The population mean is what it is. It's fixed. It has one true value. There's no sort of fuzziness in that population parameter. This represents our uncertainty in what mu is. Mu is not a random variable. It's not something that gets sampled repeatedly. It's something where there's a true value, but we don't know what the true value is, just like the age. And again, 19 out of 20 of these intervals, 95% intervals contain the true mean, and one of them will not. If you can do a 50% confidence interval, then half of them will contain the true mean and half of them won't, assuming that you have an unbiased random sample. Sound good so far? Any questions? Yeah, Leo. Is there a statistical reason why 95 is used? No, it's just an intuitive reason. It's a number that people like. We could calculate a 92% confidence interval just as easily using a table, but yeah, there's nothing special about a 95% confidence interval or about a p-value of 0.05. They're just cultural reference points. So
if you wanted to like have a really nice study, you would go and calculate 98%.
in some cases, you want to be more confident than 95% for sure. If the cost of a type 1 error is very, very high, then you'll want to be more confident than that. And there are cases where you do that, where you know, if you're betting your life on it, 95% is probably not good enough. So, yeah. This gives you an idea. So I constructed a little simulation here to show what confidence intervals from a given population look like. These are each samples that are drawn from one population with a mean mu right here. Whoops. They all are the same sample size, and the population has a given fixed standard deviation. So the things that you'll notice about it is you go, so each of these horizontal lines is a sample. You'll notice that they have different point estimates. They move from the left and the right, and they have different standard deviations. Some of them are wider, some of them are smaller, or that would be the margin of error that is varying here. And that's because there's sampling variability both in the mean and in the standard deviation that you estimate from a sample, even when they're from an identical population. So the variability in the mean is something that you can account for using a z distribution. The additional variability that comes from estimating the standard deviation from a sample is something that you can account for using the t distribution. I thought this is a nice, clear demonstration of what a confidence interval and what happens when you're estimating it. Like when you look at this one sample here, the best that you know is that your population distribution is somewhere right there, and you're off a bit. And as it happens, you got a low variability sample that was off to one side. You got unlucky in that one particular sample out of this 100 or so, or 200 here, and your inferred confidence interval is wrong. So you have to be aware that you could be wrong when you make inference from even using correct statistical methods, but you know what the probability of you being wrong is. Question?
So the ones that cross the blue line, those are 95% confidence.
All of these are 95% so the question was, are the ones that cross the blue line a 95% confidence interval? And the answer is that all of these are 95% confidence intervals. They're all unbiased, correct, random samples from the same population. The variability that you see is just due to sampling variation. Just due to the fact that if these are small samples, I think they were n equals 5. And so the variability you see in here is just reflective of the fact that in any one given sample, the estimation you make could be wrong. Because there's uncertainty in sampling variability in that sample. Another question?
Are you also saying that the probability that your confidence interval is wrong would be 5% as well?
The probability that your sampling interval is wrong is 5%. Yeah, that's correct. If it's a 95% confidence interval. Yeah. Sorry? So the red ones represent those where the sample happens to be wrong, which should be about 5% of the time. That's cool, right? Okay, yeah, the reds are just those 1 out of 20s where you're unlucky, and the 95% confidence interval does not contain the true population mean. All right, so I have some questions for you. First question, is the 99% confidence interval, will it be larger or smaller than a 95% confidence interval? Here, give me a thumbs up if you think it should be larger, a thumbs down if you think it should be smaller. Sorry?
Are you comparing both of them to the same population?
Am I comparing both of them within the same population? So I'm saying if we take a sample, just one sample, the same sample, if we calculate a 95% confidence interval and a 99% confidence interval, which of them will be larger?
Wait, what's the population?
Sorry?
What's your confidence?
Thumbs up means that the 99% confidence interval is larger.
As in like farther away from the mean, like bigger, like.
Bigger,
Or standard
bigger,
deviations.
wider.
Yeah.
Yeah. Okay, so I see mostly ups and I see one down. Okay, let me ask you this, Leo. Do you know how much that speaker weighs? No. If you were gonna bet me even money on a range, what would the range be? So if you're right, I owe you $5. If you're wrong, you owe me $5. 30 to 40 pounds? Okay. Now you're going to give me really great odds. If you win, I only give you $1. If I win, you give me $100. So then what range are you going to give?
0 to 100 pounds.
Yeah, so it's a bigger interval because you want to be very, very confident. You need a bigger interval. Okay. As n increases, oh wait, there's another one here. As the size of the confidence intervals increases, does the confidence increase or decrease? So the size gets larger, do you become more or less confidence in it?
Well, in terms of like your value being in that interval, or
Yeah.
in terms of being
Closer to the actual.
yeah, closer to the actual.
So I'm not talking about how much information do you have. I don't mean like how much, like don't think of confidence here as like your expertise on speaker weights. This is like your confidence in a range of values. So if you get a larger confidence interval, given the same amount of knowledge, you don't have any extra knowledge, would you be more confident or less confident? More confident, of course. If you say that speaker is between 0 and 1,000,000 pounds, you're very confident. Okay. So but it's less precise. No, so this is a fixed amount. I mean, this is a fixed amount of knowledge. I mean, usually when you talk about precision, you would be talking about a typical example of what I would mean by precision would be, let's say we have a scale on which to measure the speaker, a high precision scale will give you a very small interval, whereas a low precision scale would give you a larger speaker. But that's because of differing amounts of knowledge that it's giving you. One is a better instrument, it has better precision. And what I'm talking about here is your confidence given a fixed amount of information. So in that, given the same scale, no more or less precise, if it had a very detailed instruction manual, it would tell you, plus or minus this amount for 95% confidence, plus or minus this amount for 99% confidence, given the same precision scale. Those would be margins of error.
You don't have to see accuracy, right?
Sorry?
You see precision, you also have to see accuracy as well.
So there's a comment about if you talk about precision, you have to talk about accuracy as well. So precision and accuracy are two different types of measures of, two types of measurement error. They're not strictly in trade-off like bias and variance, which we're not going to get into in this class, or like precision and recall, which I think we mentioned briefly in the what was that class about the diagnostic tests. What else did we cover in that one? Sensitivity and specificity, those are in strict trade-off, but precision and accuracy, which I guess I haven't really talked about, are not in strict trade-off. Precision has to do with, like, if you think of it as a dartboard, precision means that your darts land in a small area. Accuracy means that they're centered on the bullseye. So they're different. They have to do with bias and variance. Okay, so given a fixed confidence interval, the 95% confidence interval, if we increase n, will that interval get larger or smaller? Smaller, yeah, smaller, because your standard error will get smaller, your margin of error will get smaller. Yeah. And what does the confidence interval tell us about variability of individuals in the population? Speak up. That's right. It doesn't tell us anything about individuals in the population. You could get the same confidence interval from a small population standard deviation with a small n, or with a large population standard deviation and a large n. The confidence interval tells you about your uncertainty in an estimate of the population mean. It's not about the individuals. Is that perfectly clear? All right. Here's an example which I put here for you to go through. I don't think I'll go through it in class. You'll have lots of chance to practice this in the lab and in the assignment, but here's one more example. Very formulaic factual calculation of them. Take your sample mean, take your standard deviation. If it's from the population, you use the z-distribution, that's 1.96. If it's from the sample, you'll use the t-distribution, which I'm going to get into next. All right. So how about small samples? When we use that table of z-values, it's perfectly valid either for a very large sample size or where the standard deviation is known from the population. You're not estimating it from the sample. But in the real world, where we often have small samples and we have to estimate everything from them, this is where this so-called student's t-distribution comes in. Question?
I keep getting confused.
Uh-huh.
When you say sample size.
Yeah.
Do you mean a sampling distribution constructed of a small number of groups? Or do you mean like a sample within a sampling distribution that has? Yeah.
So the question was about what do I mean by sample size? And what I mean by sample size is the number of individuals in our sample. So we go to the population, we take our random sample of people from the population. It's the number of people that we include in our study. So typically, we're only going to do the study once. So we don't get to observe the whole sampling distribution. We only get 1 point on the sampling distribution. But we know how many individuals we used to get that 1 point, that mean.
Yeah. Okay, and we were also assuming that sample mean is closer to sampling distribution mean because a sample has less variance than a population, and sampling distribution means population mean.
Sorry, could you repeat that?
You're saying that sampling distribution mean
Yeah.
equals population mean.
Sample distribution mean equals the population distribution mean, yeah.
And now the mean of all the observations in one sample in that sampling distribution is also going to be almost like the point estimate is almost equal to the sampling distribution mean too, or is our best guess, because the variability in a sample is smaller than the variability in the population, right? Those are all the assumptions.
Let's see if I have the questions straight here. I guess the question is about what's the context of what is the what are we actually estimating? Is that a fair summary?
Making connections.
Making connections, yeah. So I've talked about the sampling distribution a lot, but the sampling distribution we will never measure. We will never observe the sampling distribution.
Okay.
Yeah, yeah. It is a theoretical. It's a theoretical result from the central limit theorem that tells us when you pull one individual out of your population, measure their serum cholesterol level, you've got one measurement from your population.
Yeah.
When you pull out 10 people from the population, measure each of their serum cholesterol levels, and take the average of it, you've got 1 point from your sampling distribution. And you've got an n equal to 10. So we only have 1 point from the sampling distribution. We use the central limit theorem to give us an idea of how close that mean is to the population mean.
Okay.
All right, good. All right, I am watching you guys online. I see a couple comments, but I haven't seen any questions. Feel free to send any questions along. So this came out from this guy, William Gossett, who published under a pen name of Student because Guinness Beer didn't want him giving away trade secrets. But he noticed that the statistical methods that were available, they were developed under the large sample assumptions. And when he did things like do a hypothesis test or construct a confidence interval from a small batch of beer, it was actually inaccurate. It actually underestimated the variability in all of the rest of the batches. And this, it was the motivation for the t distribution. So if we have a known population and a known population mean and standard deviation, or at least a known population mean, we calculate these two things in the same way. So when the population standard deviation is known, you subtract the population mean divided by sigma over square root of n, which is our known exact value of the standard error for the sampling distribution of size n, and we will interpret that as a z statistic. Those values will be z distributed. If you were to repeat the experiment over and over, this would have the z distribution that you can look up in your table. If the population standard deviation is unknown, but the mean is still known, or there's a hypothesized value, which is going to be the actual case most of the time, we have a hypothesis about what that mean is, then the t statistic is calculated analogously, but the sample standard deviation is in the denominator instead.
So that's the standard error over square root. The standard deviation.
Could you speak up a bit?
You're saying that represents standard error over square root of n?
No, so the question is, what is the denominator on the right here? That's the standard deviation of the sample divided by square root of n. And that denominator is the estimated standard error. So in both cases, the denominator is the standard error. On the left, it's calculated exactly from a known standard deviation. On the right, it's approximated from the standard deviation of the sample. So sigma and mu.
See, that's what we're the standard deviation of a sample is the standard error.
No, the standard deviation of a sample is not the standard error. The standard error is the standard deviation of the sampling distribution. S, the standard deviation, that's a variability of individuals. So it approximates the population standard deviation, and it is not a standard error.
And then you said if for Z, your mean can be unknown, right? The population mean. Because you can estimate it.
So the question was, for Z, the population mean can be unknown. If we are, if in the realm of confidence intervals, like we're talking about today, the population mean is unknown, and we're inferring a range of them. Once we talk next class about hypothesis testing, the hypothetical population mean is known. That's called your null hypothesis.
So we will be using Z-test, but in a different way.
Right. Next class, we'll still use Z, we'll still use T, just in a different context for hypothesis testing rather than estimation.
So these unknown population in our hypothesis, and the T's will unknown population or unknown sample.
So just to repeat the comment, we use Z when the standard deviation of individuals in the population is known. We use T when it's not known and it's estimated instead from the sample. Question? When would we ever know the population standard deviation? We might know the population standard deviation if it is something that was on a census. So we have a reference from everyone. In some cases, I don't know, like the IQ test, it's designed so that for everyone who takes the test, it's put on a curve so that it has a given standard deviation. There are cases where you might know the population standard deviation. The t-test is more common, yes. In public health studies, in the literature, the t-test is much more common than the z-test.
Is it a stronger variable to use?
What's that?
Is it a stronger variable to use? Score.
Is the stronger variable?
I don't know if that's the right way to say it, but it will try to calculate how much it's sort of- do I have a better calculation of the t statistic?
Oh, so the question was, do you get a better calculation using the z or the t? The answer is just that z is correct when there is no uncertainty in the standard deviation. T is correct when there is uncertainty in the standard deviation. You saw how in that figure a little while ago, different samples, you'll get different estimates of the standard deviation. The result of that is that you end up with a larger confidence interval. So unless your sample size is really big, like 300 or something like that, your t-based confidence interval is going to be larger than your z-based confidence interval. You don't have as much information. So you could say that the t is more conservative. However, it's actually wrong if you are using a population standard deviation, because you want your 95% confidence interval to contain the true mean 95% of the time. You don't want it to only contain it, or you don't want it to contain it 99% of the time, because then you could have made your interval smaller. You just want it to be, you want what you say the confidence to be to actually be your confidence. So it depends on where you get your standard deviation of individuals from. Yes, question.
So the sigma in the Z statistics is for the standard deviation sample, right? In the lower standard deviation of the population. And S is the standard deviation sample in the abnormal standard deviation of the population.
Yeah, so there was someone just pointing out that sigma is the standard deviation of the population, S is the standard deviation of the sample. S is the standard deviation of the sample.
But what about sigma is also standard deviation of the sample?
No, sigma is the standard deviation of the population. So there's no uncertainty in sigma. You've used every individual in the world to calculate sigma, or every individual in your population. So both sigma and S relate to the variability of individuals, but sigma is the truth based on everyone, and S is the estimate from a sample.
So T statistics will be more for like representing the samples, and Z will be more for the population.
So the question was, T is related to statistics from samples and Z for the population.
What's in T and Z for the
So what are T and Z going to do for us? That's well put. What are T and Z going to do for us? Both of these, we're going to use them to represent a sampling distribution. And we're going to use a sampling distribution for hypothesis tests and for confidence intervals. In this class, we're going to use several different sampling distributions. We'll use Z, we'll use T, we'll use a chi-square distribution later. I don't think we're going to get to any other distributions. But the way that we ordinarily use a sampling distribution is that in hypothesis testing, we will calculate one of these statistics, z or t or later chi-square, for our sample, and then we will calculate what is the sampling distribution under our null hypothesis and calculate the probability that our sample came from that sampling distribution. So this, what it does for us is it tells us what range, what the probability of getting any particular average for your sample is, given some null hypothesis.
And T is,
T is the same thing. It's just a slightly different thing that you calculate from your sample. So you could take the same sample of 10 people, and if we happen to already know sigma from the population, then we can hypothesize that that we know the sampling distribution to be z distributed. We take that same sample though, and if we have to estimate the standard deviation from the sample, then given the same population mean, we expect a sampling distribution to follow the t distribution. So the point is that as you take repeated samples, from the same population, there will be variability in them. If you get some really large mean, for example, then you can infer that it probably did not come from that population. And in that case, you would reject your null hypothesis. And the z and the t are the basis that you use for making that decision. That's okay. Keep asking. This is an important class, so don't worry about asking lots of questions.
are you like comparing Z value and T value and see how close they are and see if they are?
Are you comparing z and t value? No, we won't compare the z and t.
That's only for the two different hypotheses, right? Because you have this null and unknown standard deviation calculation. So they are basically using two different scenarios.
The z and the t are used in two different scenarios. That's right. Is there another question? Yeah.
I know the standard deviation population.
Yeah.
I know everything. I don't get what's going to be.
Okay, so if you know the mean and the standard deviation of the population, you don't get the point of the z-test. How about this for a point of the z-test? We know the mean and standard deviation of the birth weights of infants in the United States. It's, I don't know, 7 pounds plus or minus half a pound. Now, I'm going to look at some potentially different population. I don't know if it's different. Suppose I'm going to look only at mothers who ate rutabagas during their pregnancy. Okay, and now I want to know if this sample I took from that population is likely to have come from the main population or not. So, and if you have a small sample, you could reasonably make the assumption that the standard deviation is the same as the population and just do a test on the mean. And if you decided to do that, you would use the z distribution. If you decided instead to estimate both, to estimate your standard deviation from your sample, then you'd use the t distribution. Mm-hmm.
Question. These both tests are talking about, you said, population and sampling distributions. But because sampling distributions are so close to actual population, at least in terms of mean, then you can make statement in the end like, from this we infer blah 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 about population distribution, not sampling distribution.
So
And
just,
therefore, our population looks like that.
um,
Are you trying to get there or not?
let's see. I'm not sure I can recapitulate this question for the online people. But it was a question, I guess, about what are we inferring. My first comment would be careful about your terminology there, because I heard you say things like the population sampling distribution.
Sorry, no, I meant sampling distribution.
Okay, sampling distribution. We're not going to do inference about the sampling distribution per se. Keep in mind that the sampling distribution is an imaginary construct.
So we're never ever dealing with it. That was just to
We're-
explain.
We are dealing with it. We're dealing with it to do inference about the population. So usually what we care about is a population. What we have is a sample. We only have one sample in a study, but the sampling distribution tells us about the probability that that sample came from this population, or that two samples came from the same population. So the sampling distribution is an imaginary thing that tells you about what you would see if you did an infinite number of experiments, right? It's not a real thing, but it's a very useful thing, and we do use it for constructing confidence intervals, for doing hypothesis tests. You remember that picture of all of the confidence intervals? That was like a demonstration of the sampling distribution, how in repeated sampling you get different means every time, and that distribution of means is your sampling distribution, even though we're only ever going to do it in a simulation on a computer to actually see what it looks like.
So I guess, okay, this will help me. If you had a graph on which you were calculating these intervals,
So if I had a
what would be
graph
the
on,
X and the Y?
if I had a graph on which I was calculating the confidence intervals,
Yeah, what would the X and the Y be?
what would the X and the Y be? Well, a confidence interval is typically just one-dimensional. So it's like if we're calculating a confidence interval for infant birth weights, it's just one dimension, it's weight. It's got a minimum, it's got a maximum, it's got a central point estimate. I used two axes previously just to show a bunch of different samples.
Gotcha.
Yeah. Okay. So this is just recapitulating the last slide. The standard error is the standard deviation of a sample divided by the square root of n. Well, if this is how we calculate the standard error, estimate it, then we're going to use the t-distribution. Point being that this is S here. It's estimated from a sample. Oh, man. So even if we have a normally distributed population, okay, as we take small samples and calculate t using the equation on the previous page, so the sample mean minus mu divided by the standard error, it's not going to be normally distributed unless n is very large. And I don't mean 30, I mean like hundreds here. It's not normally distributed, it's t-distributed. And the t-distribution, unlike So the normal distribution, it had two parameters. It had a mean and a standard deviation. That was it. The t distribution has a mean, it has a standard deviation. It also has a degrees of freedom. So I should say for our purposes, the z distribution, it only has it has mean 0, standard deviation 1. So there's no, like, you know, those are fixed. The t distribution, however, has this extra thing, the degrees of freedom, that will change the shape of it. And the t distribution is different for every sample size. So, and as you'll find out, the smaller n gets, the wider that t distribution gets, the more spread out it gets. Question is, what is n minus 1? So why are the degrees of freedom n minus 1? I do have a slide on this later, but you can think of degrees of freedom as, there are a couple of ways to think about it. One way would be, how many of the data points could you hide and still figure them all out again based on having the statistic? So in the case of the t statistic, if you know the t statistic and you were to lose one of your data points, you could figure it out again. And so that's why it's n minus 1 degrees of freedom. Let's see, is it on this next page? No, not on the next page. But it's in maybe the simpler way to think about degrees of freedom is how many additional data points do you have than you need to calculate this statistic. So for t, the absolute minimum that you could use, let's see, would be, even I have a hard time. I have a hard time thinking of it that way too. I guess it'll make more sense once you calculate a couple of them by hand. How you'll use, if you have 5 data points, you'll use all of them to calculate the mean and the standard deviation. But from either of those, if you were to take away one of them, there's only one value that could be there to give you that same mean and standard deviation. If you took away 2 of them, then there would be several values that you could put back in. If you put one of them back in, you could invent another value in the other one that makes it work.
I guess it just means that it's less complete collection of data population. So you could
it's a less complete collection of data than what?
I don't know what I'm saying. Because you said, like, for Z statistics, you basically you know the whole population's standard deviation, and you use all the data. But for T statistics, you do not know the standard deviation of population, so you kind of just pick, the sample, any sample from the population. You test the standard deviation, the mean, so the degree of freedom, just because you're not using the whole population data, so you have
Yeah, you are, I mean, for a t test, you need at least 2 data points to estimate the standard deviation of your sample. So the fact that so if you have 2 data points, you can get a standard deviation. If you had 1 data point and your standard deviation, you can figure out what the other data point was. That's why it's 1 degree of freedom.
You say if you know one t statistics.
Or if you know,
deviation,
yeah, if you know the t statistic and it was calculated from just 2 data points, then you can figure out what the other one is. Because imagine you have the mean of the 2 data points and you have 1 point. You know, I wish I could draw on this table, on this thing, but what's that? Use the blackboard. Then I'm gonna have to lift this up though. But you have okay, let's suppose we have 2 data points. They're 10 and 20. The mean is 15. Now, and the standard deviation, I don't know exactly what it is for that. It's somewhere less than 5. But now, if you have just the mean in one of the data points, you know what the other data point is. And if you have the mean and the standard deviation, you know, or if you have one of the data points and a standard deviation, you know what the other data point was. And also the mean, that's right. So you can take away 1 data point and recalculate everything. And right, 1 degree of freedom. If you calculate a bunch of different things from your data, then it turns out you can take more of them away and still recalculate them because of these extra things you've calculated from them. And the amount of data points you can take away is your degrees of freedom. So the normal distribution and the t-distribution look similar, except that the t-distribution is wider. With very large degrees of freedom or large sample size, they'll look almost identical. The smaller the degrees of freedom gets, the wider the t-distribution gets. This is from your textbook, the Open Intro Stat book, and this is a table of the t-distribution. So what it's giving you, here's what the t-distribution looks like. It gives you a 1-tail and a 2-tailed probability. And you'll notice that the 1-tailed version is always half the probability of the 2-tailed version, because you're looking at one of these shaded areas, either the left or the right, instead of both. And this is telling you, so for 1 degree of freedom, let's look at the 1-tail probability of 0.025, 2-tail of 0.05. This is the so-called critical value, 12.71. This means that the area under the 2 tails, if you go less than minus 12.71 and more than 12.71, is 5%. And as you increase the degrees of freedom, notice this gets smaller and smaller. The distribution's getting narrower. At n equals 30, it's down to 2.04. It's not until all the way up at n equals 500 it gets down to exactly 1.96, 2 decimal places, which is what you would get if you looked up the 1-tail probability for 0.025 from the z distribution. So that's what I mean, that this is not just the n equals 30 definition of large sample here. We're almost done. Here was the answer to your question a few slides later, the number of independent observations that you use to calculate the statistics minus the number of parameters that you estimated. It's a little bit tricky for the t. We do estimate sigma and the sample mean, but they go together. You can figure them both out without using extra degrees of freedom. Or this alternative definition that I like, the number of observations that you can recover if lost, based on the statistics that you calculate. Almost done. Oh, there's a question from online. Oops. Where does the n-1 play into the formula? Let's see. So I suppose you're talking about this formula. And the n-1 doesn't play in here yet. The n-1 plays into what the distribution of these t's are in the sampling distribution. So it doesn't go into the calculation of t. It has to do with what the distribution of t is across repeated samples. I wish Hangouts would offer me a way to answer a question without having all those infinite mirrors come up. So we're making the assumption of a normally distributed population here when you use the t procedures. As long as the population is normally distributed, you can get a correct confidence interval using this formula with the t distribution. And here is where the n-1 will come into here, and looking up this critical value of t from a table. So this t is something that you'll look up in a table. We'll use t for doing confidence intervals today, and we'll use it for hypothesis testing next class. Here's an example for you to take home. We're not going to do it right now in class because I want you to be able to get down to the lab. We're a little bit late now, but if we've got 5 glasses of beer from a relatively inconsistent brewing process, they have these different alcohol volumes. What is the 95% confidence interval for alcohol content of beers being produced by this process? That's a confidence interval estimation problem. Alternatively, is there evidence against the null hypothesis that the mean alcohol percent content of all beers produced by this process is 5.0? That's what we'll do next class. Keep in mind these assumptions. I want you to get downstairs, so please look over this on your own about the robustness. It's important to keep in mind that the T procedures, the two-sided T procedures, are robust. We haven't talked about one-sided procedures yet. They're less robust, but the two-sided ones are very robust. That is that if your assumptions are violated, your population values are not normally distributed, you'll tend to be conservative. Your confidence interval will be larger than it needs to be, or your p-value will be larger. couple rules of thumb for when to use the T procedure. Depends on how normally distributed your population is. You'll do histograms, you'll do descriptive statistics to make that call about how normally distributed your population is. And these are just some rough rules of thumb about when you can still use them. You know, if it's not totally normally distributed, you might still use them as long as the sample size is greater than 15. Even if you have very skewed distributions and outliers, you're still going to get a pretty good estimation from the T procedures as long as n is greater than about 30. Of course, the assumption that the data are a statistically random sample is always important. If that's not the case, then nothing can help you. Long class. Here are a couple questions to think about. Think about these at home. We'll start the next class with these questions, all right? Okay, let's head down to the lab. Thanks for hanging in there today.